Hello everyone, today I'm presenting my work Meta-RegGNN predicting verbal and full-scale intelligence scores using graph neural networks and meta-learning. This work has been done at Basira Lab by myself, Dr. Iman Jram, and supervised by Dr. Islam Raqiq. Research has shown that subjects with autism spectrum disorder (ASD) have higher rates of health issues throughout childhood, adolescence, and adulthood, and this can lead to a high risk of early mortality. ASD diagnosis remains a challenging task due to the wide range in the severity of its symptoms and the lack of pathophysiological markers. Intelligence in particular is a key aspect of ASD. In fact, the brain network structure is described by functional brain connectons that are derived from resting state magnetic resonance imaging. Brain networks are modeled as graphs, where nodes represent ROIs and edges encode the relationship between ROI pairs. It could be functional, structural, or morphological connectivity. So the problem that we aim to solve is how to predict behavioral scores such as intelligent IQ scores from the human brain network. However, addressing such problem has several challenges. Let me first give you an overview of the state-of-the-art methods and the order of works that try to solve this prediction problem. This includes a Nature protocol paper which trained the linear regression model using cross-validation to predict behavioral scores from connectomes. This method has been outperformed later by a machine learning-based technique which aims to study how neural correlates of intelligence scores are altered by autism. However, these methods flatten the brain connectome matrix through vectorization, which neglects the graph structure of the connectomes. To solve this issue, graph neural networks (GNNs) have been proposed. They can handle complex graph data and have proven their exclusive ability in learning in non-Euclidean spaces, including graphs with complex topologies. For that, Haneke et al. Proposed RegGNN that regresses brain connectomes to a cognitive score using a learning-based sample selection method. However, this model cannot handle domain shifts in training and testing data distribution. Overall, the standard learning approaches fail to solve the domain fracture problem. To decrease this domain shift and improve the generalizability of proposed methods, Finn et al. Proposed meta-learning that aims to rapidly learn a new task from a small amount of new data. The basic idea of meta-learning lies in taking a small number of training samples to train the model, and the remaining samples are considered as testing samples. And I want to remind you that these are actually training samples, so we simulate the training and the testing during the training phase to learn different tasks. To explore the graph structure of the connectons, our Meta-RegGNN framework is based on the conventional RegGNN network that consists of two graph convolution layers and a fully connected layer to predict behavioral scores. The conventional method is trained in a regular way where the whole dataset is fed into the RegGNN network. To decrease domain fracture issue, meta-training is implemented as episodic tasks on support and query sets. A few-shot learning framework is used for the query set. The goal of this few-shot regression is to predict behavioral scores from only few samples after training on many samples with similar statistical properties. So, we first find the RegGNN model parameters that are responsive to modification in the support training set. For that, let us consider our regression GNN model represented by F that maps brain graphs G to behavioral scores S and parameterized by theta. Theta is updated when adapting to a new task to theta prime as follows, where gamma represents the step size hyperparameter and LT denotes the loss function of any task. Then, the meta-optimization through tasks is conceived in order to randomly choose k samples and update the regression GNN model parameters theta as follows, where eta presents the meta step size and SE represents the loss function. During the meta-testing, predicted behavioral scores are obtained using unseen samples that are provided with the optimized weights obtained from the meta-learning stage. For testing our framework, we used 428 subjects from the OBIDE dataset. Each subject is represented by a verbal intelligence quotient (VIQ) and a full-scale intelligence quotient (FIQ) from functional brain connectons. To evaluate the effectiveness of our Meta-RegGNN, we used threefold cross-validation based on empirical observations. We trained our proposed method for 300 epochs. For the meta-training, we used one gradient update with k equal 5 shots. We benchmark our framework against the first and unique deep learning method proposed in the literature, RegGNN. To test our method, we state the mean absolute error MAE and the root mean squared error RMSE. These results present the average of more than 40 random repetitions. Our framework captured complex topological patterns of the brain graph and achieved a good trade-off between flexibility and performance, requiring fewer samples for training. Moreover, it can deal with test samples that are different from those of the training samples, such as brain diagnosis with Alzheimer's disease. Compared to the anti-cohort, the ASD cohort achieved the worst results across all methods. The difficulty of predicting behavioral scores in the ASD cohort may be explained by the high inter-subject heterogeneity. In conclusion, in this work we introduced the first regression GNN network through meta-learning, namely Meta-RegGNN, that regresses functional brain connectomes to predict cognitive scores. We contributed studies with introducing a novel meta-learning regression GNN that shows an exclusive ability in incorporating topological properties of the functional brain connectomes to predict behavioral scores, and presenting the first work on meta-learning for regression GNNs, which boosts the prediction performance by decreasing the effect of sample heterogeneity. In our future work, we will investigate the explainability aspects of our Meta-RegGNN in order to identify connectivity biomarkers distinguishing between typical and atypical brain states. Feel free to check our recent review paper on GNNs in network neuroscience covering recent GNN architecture for brain connectivity, integration, classification, super resolution, and more. You can also visit the GitHub repo of the paper. For more, please visit us at basira-lab.com.